All right, so let's do that. Let's take, we're going to start with this alkene, and we're just going to go around this reaction wheel. All right, so let's start here. We got an alkene that we're starting with here. And we've converted it to an alcohol, but where's the location of that OH group matters. So where's that OH in relation to the alkene? Is it Markovnikov or anti-Markovnikov? And what, if you answer that question, tell me what the difference is. Well, okay, let me ask this question. If it was Markovnikov, where would the OH be? Based on the alkene.
Substituted carbon.
On the most substituted carbon in the alkene. So here's my alkene right here. So if it was Markovnikov, it would be here, right? So that means if it's here on the least substituted carbon, it's got to be anti-Markovnikov. Okay, so now that's a clue. How do we make anti-Markovnikov alcohols from alkenes? Well, we have three ways of making alcohols. One way we can rule out because it makes diols. That's osmolation, OSO4, and then NMO. So we rule that out because that's going to give me a diol. I don't want a diol. I want an alcohol, but I want it on the with this regiochemistry, right? On the least substituted carbon. What are my two methods for making alcohols from alkenes? My two other methods. Anybody? I got two methods for just alcohols, not diols. Oxymercuration is one method. What's the other method? Is that the other method? Hydroboration, oxidation. So which one of those is Markovnikov and which one is anti-Markovnikov? We got two additional people in the room now. One of those two people should have an answer. Because remember, these two, they both make alcohols, but they have a different regiochemistry. So which one is Markovnikov and which one is anti-Markovnikov? Y'all are like my 9 o'clock class. The silent majority. You remember that the mnemonic that I gave you? Mercury is Markovnikov. Boron is anti-Markovnikov. It was in the one of the most recent videos I said. All right, anyway, so what are my reagents here? I'm making an anti-Markovnikov alcohol from an alkene. And I know it's hydroboration / oxidation. I know that. Because that's the way you do that. What are reagents? Two sets of reagents I have to use. If you got your notes in front of you, you should be able to tell me this right away. If you have that overview sheet, you should be able to tell me this right away. If you have flashcards, you should be able to tell me this right away.
Peroxide and sodium hydroxide.
Okay, that's the second step. I agree. What's first step? You're right.
BH3 and THF.
Yeah, so BH3 and THF. This is my solvent, THF. Good. All right, so if I want to make an anti-Markovnikov alcohol, from an alkene, right? The start material matters. So this is my tool for doing that. Hydroboration followed by oxidation. All right. Oh, let's do, okay, so let's do the next one. Let's do this one. I want to take the alkene and make it into a diol. So I have an OH here and an OH here. Each carbon in the alkene has an alcohol on it now. What are my reagents for that? Still in the same wheelhouse of making alcohols, but I want to make a diol. Anybody? We're going to talk about this. We do this reaction the other day. Yes. Yes, right here. Right, if I want to make an alkene into a diol, I need to do osmolation. I need to do osmolation. So the reagents are here. OSO4, osmium tetroxide, that's in step 1. And then in step 2, sodium hydrogen sulfide. Flashcards, man, flashcards. I can't stress it enough. So osmium tetroxide and then sodium hydrogen sulfide. All right, let's go to, let's see. Yeah, let's do this one. What do I need to add to that alkene to get this alkyl halide? And I guess the other way to say that is, how do I make alkyl halides from alkenes? If I want to add a hydrogen to one side and a halogen to the other side. How do I do that?
Would you add HBr?
Excellent. I'll add HBr. And then, can you answer this question? Was that you, Mike?
Yeah.
Why does the bromine go here on the most substituted carbon? What's the regiochemistry for that?
Is it very planar?
Say again?
Very planar? Or is that something else?
No. It's, think about what we just talked about. Markovnikov or anti-Markovnikov. This reaction follows Markovnikov regiochemistry. Right. So the bromine is always, the halogen always goes to the more substituted carbon in the alkene. Because if you remember the mechanism, you make a carbocation intermediate, like the double bond breaks, and it attacks HBr, and you get a plus charge on one of the 2 carbons. So, all right, let's do this one. I have over here a halohydride. How do I make that from this alkene?
Br2 and H2O.
Excellent. So bromine with water as the solvent. Let me put it under arrow. Right, good. That's exactly right. Halohydrins they follow the same mechanism as halogenation. Only difference is how the bromonium ion, the intermediate, gets popped open. Usually, if you do a Br2 by itself, then the other bromine will just come in. But with halohydrin synthesis, water opens the ring. And if you notice, again, trans stereochemistry. Right, the OH and the Br are on opposite sides. Just like if it was a halogenation, the two bromines would be on the opposite side. All right, let's do, let's see, this one. So the methyl group is going back because I added hydrogen to the front face of that alkene. That's why the methyl group is going back. So there's actually a hydrogen right here on the same face as that alcohol. But I have an alcohol and it's not on the most substituted carbon. What are my reagents for that? I want to take that alkene and turn it into an alcohol. The alcohol on the least substituted carbon. We just did that up here, is that right? Right here. Anytime I want to put, keep in mind, we only care about the alkene, the double bond. That's what's reacting. So anytime I want to put an alcohol on the least substituted carbon in the alkene, this is the method that I'm going to use. Hydroboration followed by oxidation. So it's going to be that's my reagents for that. What about here? Even though I don't have it in a box, before I get here, where I just totally get rid of that double bond. Anybody? What can I add? What have I added to that alkene to get rid of the double bond? How do I do that? I want to add 2 hydrogens to the alkene. There's a method for it, and we talked about it already. Need some Jeopardy music. Anybody? How do I add a hydrogen to each carbon in the alkene?
Would it be hydrogenation?
It's a hydrogenation. Good. And what are the reagents for that? You're right. So it'd be hydrogen gas and
And
go ahead,
platinum?
platinum or palladium. Both of those catalysts work. But that's how you would do that. The only thing that we haven't talked about up to this point, or two reactions that we haven't touched yet, is the one here highlighted underneath that halohydrin, and then Simmons-Smith. Those are the only two reactions we haven't discussed. This reaction right here is the result of what we call an ozonolysis. Right, and I'm going to take some time to talk about that. Some time to talk about that down here. So ozonolysis is a way to convert alkenes into carbonyls. Right. Basically, without going through because it's a very involved mechanism. And I think I sent that video already. And I don't want to go because it'll be the rest of the class if we went through that mechanism right now. But basically, both carbons in the alkene, let me just write it out like this. Both of those carbons are going to become carbonyls. Right? And just visually, it looks very simple. Right? The way that I teach this and the way that I help students remember this, what happens here is kind of twofold, right? You can visualize cracking this double bond in half like that, and both pieces becoming carbonyls, or you can write the oxygens in. Right? You can write them into the double bond. So that's normally what I'll do. I'll take that double bond and I would just put an oxygen here and one here. And then that's how I know what my carbonyls look like. But it's a way to convert alkenes into carbonyls. So it requires two steps. The first step is ozone gas. Second step is zinc metal and acetic acid. Right? And that will take this carbonyl, I take this alkene and crack it. Crack it in half. So each carbon in that alkene becomes a carbonyl. That's why you see a double bond. I mean, that's why you see a carbonyl here and a carbonyl. We change the color here. Right, you can see that this carbon right here with the methyl group attached. That's here. And then the carbon here with the hydrogen attached. That's here. All right, so ozonolysis is, you can do ozonolysis on any alkene. Even if you have multiple alkenes, all of them will get touched. And I think I mentioned when we first started talking about the reactions and I was going over like the different reactions, I think I mentioned that the ozonolysis, the traditional way to do it was quite dangerous. Because you're taking oxygen gas and you're converting it into ozone prior to pumping it into a reaction vessel. Because I mean, it's a gas, so you'll have a flask, you'll have it sealed up. You got a blast shield in front of your ozonizer, And it's just a really painful and cumbersome reaction to do, but it's doable and it works. It works wonders. Questions about that? So the reagents for ozonolysis are ozone gas first, and then the second step, zinc metal and acetic acid. All right, any questions? I'm gonna leave this for you all to do. Right, remember the rule. So right here you have a group 5. You got 2 nitrogen, so you're going to add 2 to HREF. For every group 5 element, you'll add 1 to HREF. So when you calculate HREF, since you have 2 nitrogens, you have to add 2. And then right here with the bromine, you're going to subtract. Otherwise, you're going to get a fraction. And remember, this is HREF minus H molecule divided by 2, and HREF is 2N plus 2. Where N is the number of carbons. Right, so y'all can calculate those, and we're going to move on to some more reactions. Same here. All right, let's look at this right. These carbocations right here. The question says, rank them in order of increase in stability. And it says least stable is 1, most stable is 3. And don't worry about the points. This is just from an old handout, and I just cobbled it together with some other material. Which one is the most stable out of all 3 of these? This one is secondary. This one is tertiary. And this one is primary. So which one is the most stable?
Is it tertiary?
Tertiary. So that's going to be ranked as 3, right? 3, 1 is the least stable, 3 is the most stable. So which one is the least stable?
The first one?
The secondary one? When you say first, you mean the one on the left or on the right?
The one on the right.
Oh, okay. All right. Yeah. So this is 1. And then over here, this is going to be 2. Why does it matter that we're talking about carbocation stabilities, you know, in reference to alkenes, right? The reason is because if you add, there are certain reactions where you're going to get a carbocation intermediate. And so you need to understand carbocation stability, which carbocation is more stable or less stable. A lot of times will determine the regiochemistry of a reaction, where something is going to add. Because a more stable carbocation, that carbon is more electrophilic, more likely to be positive than a less stable carbocation. All right. I think we talked about halogenation. I want you to work through that one. Let's go to, let's answer these questions right quick. If a mechanism is stepwise, what does that mean? If we say it's stepwise,
It has more than one component.
multiple,
It requires multiple steps.
yeah, it has multiple steps. It does not just proceed through a single step, right? If we look at the energy diagram right there, what does that energy diagram say to you? How many steps are in that reaction?
1
One
or
step.
2?
No,
Oh, 1.
you're right. Look at what it says. Reactants to products with nothing in between. Right. So there's only one step. So would that be concerted or stepwise?
Concerted.
It's concerted. Is it endothermic or exothermic? I figured I'd throw that monkey wrench in there just to see where we are. Is it
Endothermic.
endothermic? Good. Handwriting's atrocious today. Or every day, but today is unseasonably worse. It's endothermic. Good. What is KEQ if it's endothermic? Is it greater than 1 or less than 1? And is delta H positive or negative?
KEQ is less than 1.
Good. Is delta H negative or positive?
Positive.
Good. Less than 1. Delta H is positive. All right. I'm just refreshing you. All right, let's look at the next question. Which of the following reactions shown below would the reaction energy diagram best represent? Forget about the reactions. Well, don't forget about them, but this is the clue right here. Any reaction that proceeds through an intermediate before you get to product is going to have multiple steps. Is that right? Because the intermediate is a step in between the start materials and the products. So which one of these is going to be represented by that energy diagram up top?
Two.
2. I agree. 2 would be considered concerted, right? Because it doesn't go through an intermediate. And 1 and 3 are both stepwise. Anybody not catch that? All right, let's do yeah, I'm just gonna walk this down. Let's go to here. The first reaction, OSO4 and NMO. Is osmolation. What's the product? Yeah, you should definitely have a flashcard with this on it. Anybody? What's going to happen to my double bond?
Your double bond will break and there'll be an OH on each carbon.
And what's the hallmark? What's the key characteristic? Because those OHs can be on the same side or they can be on opposite sides. But what do we know about osmolation? Like the stereochemistry that we can say is definitively characteristic of osmolation. Right, the alcohols are always on the same side. So we call it either syn or cis. All right, let's go to here. We got bromine and water. It's a halohydrogen synthesis. What is the product? We just did this like a minute ago.
Bromine would be on the least substitute carbon.
And then what's here? OH, is that right? All right. Here, what is MCPBA and what does it do to alkenes? Notice all I'm looking at is the double bond here. Here, I don't care about anything else that's attached. All I'm looking at is what's going to happen to the double bond. MCPBA is one of our reagents to do what? It's epoxidation. What is an epoxide? What is that going to look like?
Will it have like a triangle, the oxygen, as the P?
It's a three-membered ether. Yes, I agree. Right, so each carbon in that double bond is going to end up with a single bond to oxygen. An epoxide is what it's called. It's a cyclic ether. All right. How much time we got left? We'll let y'all go early today, I think. Let's do that's the same question. Let's do number 9 and we can stop. We're just picking the reagents. If I wanted to go from here to here, right? What did I do? I made an alcohol with Markovnikov regiochemistry. What are my choices up here? Of the choices that I have, don't worry about A and C. We're gonna do those last. So it's got to be B or D. Which one is it?
B?
D. Okay. So B is hydroboration, right? This is, remember, this is anti-Markovnikov. So it got to be D. Oxymercuration. So I'm gonna put that here. It's got to, because the alcohol, if you look at the alcohol itself, it's on the most substituted carbon in the alkene. And the way you get that is through oxymercuration. So then what about this one? Notice where the alcohol, the regiochemistry is different. The alcohol is now on the least substituted carbon in the alkene. So then this would have to be what? That would have to be B, right? Which is right up here. This would be mercury acetate and water, followed by NaBH4, sodium borohydride. Right, so that's Markovnikov addition, and then the other is anti. Remember, the oxymercuration as well as hydroboration both do the same thing. They add H and OH across the double bond. The OH is going somewhere, the H is going somewhere. That's the essence of the reaction. Now, it's not that simple, but this is the way to think about it. All right, what about this example right here? What reaction is that? I took the alkene, I cracked it in half, and I turned both of those carbons in the alkene into carbonyls. So it's ozonolysis. It is ozone gas followed by zinc and then acid. I'll give you a pass on that because this is our first time seeing this today. And then the last reaction, which is here, is notice there's a 3-member ring in the product. It's a cyclopropane ring. The way you make that is to do what's called the Simmons-Smith reaction. So it's this set of reagents right here. So the Simmons-Smith reaction, you take an alkene and then you react it with diiodomethane, and then in the presence of zinc, and you get a this is a really interesting reaction too, because it proceeds through what we call a carbene, which I only have 4 minutes, so I don't really want to get deep in the weeds on that, but I'll send a video with the mechanism. So it goes through what's called a carbene. And then the outcome is a 3-member ring, a cyclopropane, which is a very important functional group in nature. Very, very important. All right, we got to stop here because I only got 4 minutes, and I said I would let y'all go early. So I'm gonna be a man of my word and do that. Any questions about anything? I know this was a lot today, but I promise you, you got to make some flashcards and you got to get that overview sheet and just walk through it and find out where your questions are so you can ask them. All right, any questions about anything?